Okay, so, oh God, no, I opened the wrong file, so let me just go back. This is strange. It shouldn't take so long to load. Sorry. Thank God. Okay, so today we will again study motion in one dimension, and we'll be focusing on Newton's laws. And so it's actually very, so we saw last lecture, we saw a large family of dynamical systems where we said you consider X to be some big n-dimensional vector. And we wrote some system of this variety where there was some bunch of n functions of X at t. It's a fairly general dynamical system, and n can be odd, for instance. There's nothing special about it. So, okay, but if you look at Newton's equations, when we repackaged it, we found that it was for Newton's equations are a special kind of so for the instance of a particle moving in a potential, there's only one function we needed to give, but here you see we have to give n functions. Okay, so there are n functions. So in Newton's equations, we saw that first thing is that it's a dynamical system with even phase space is always even dimensional. It's 2 times the configuration space or position space. So it's even, which so that is not true. I mean, in a generical, so it's not generic dynamical system. It's a dynamical system with even dimensional phase space, number one. And instead of n functions, I just have to give you one function called the potential, for instance, for the example that we considered. So it's very, very special. Okay. And one might wonder, is this, does this mean that we are, by studying Newton's equations, we are losing out a lot? The most interesting thing is that a large family of systems at a fundamental level are of this kind. We'll generalize Newton's equations to something called Euler-Lagrange equations or Hamilton's equations of motion. And so what we will find is that it's enough to give one function or instead of giving n functions. Okay, so it's pretty. So at a fundamental level, that's what is happening. But of course, there are systems where the more general dynamical system approach is used. So today we will focus on motion in one dimension, and if time permits, I will do something in higher dimensions. Okay. So consider the motion of a particle of mass in one dimension with coordinate x moving under the action of a force field f of x. So Newton's equations is very easy. It's just ma equal to f of x. And when the force field is conservative, then f of x. So here, so f of x is minus dvx. So there's only one function potential that we have to do. Okay, so then the equation. So this is for conservative. So So that's what we get. And then one integration can be done very, very easily. You just multiply this thing by dx by dt. And then you will see that the left-hand side becomes m by 2 d by dt of x dot square. Okay, and right-hand side becomes minus dv by dt. And remember, v of x is time-independent potential. Okay, so this is important. Okay, so this is what we get. We get something like this, and you can rewrite this whole thing as taking this to the other side to write it as d by dt of you must have seen this many, many times, but then you can integrate. This says that this quantity in braces is a constant, and that constant is what we call energy. So energy appears in the setup as a constant of motion. So this is something which you would have seen many, many times. I'm just doing this to set up the formulation, etc. Okay. So any questions, comments? Okay. So next step would be to actually solve this differential equation. But the advantage here is that in this case is that one integration is all trivially done, so we can use this equation. So E is some constant, so we can think of E as one of the quantities that are given. So in the beginning, okay. So E is a constant. Okay, so it's so we can rewrite this by taking it to the other side, x dot. So that you will get x dot square equal to something, but then if you take this, there are two possibilities: plus or minus square root of 2 times E minus V of x over M. Okay. So this is just the same as previous equation. Okay. So, but the point here is we have to give a value of E. Okay. So here in this picture here, I have chosen. What I have done is to choose some random potential. So this black line here, one second. So this black line here, this one, okay, is the potential. So and then what I have done is so what it says. This only makes sense that we have to give one quantity E. So you have to specify the values of E, and so that's what one is doing here. And so so let's look at one example. So I have chosen a value E1 first. So I just draw a horizontal line. So this is what is drawn here is V of x versus x. Okay. So what I've done is drawn a horizontal line with this energy E1. And so the first thing you can see is that if you come to a region, in this region, what happens, I've indicated that it's not, classically it cannot go there because in this region V of x is greater than E, so x dot becomes pure imaginary as a formula, but what it means is that it's a classically forbidden region. Okay, classical means, so one more thing, whenever we use the word classical in physics, it doesn't mean like, classical literature like, Shakespeare or something like that. It means not quantum. Is that clear? Classical in physics means not quantum mechanical. Okay, so let's just go back one slide and look here. So what you can see here is if you look here, if V is greater than E, so there is a problem. We cannot solve this because this quantity is always positive. And so if you take this to the other side, you get E minus V of x. So what you will get is, so it cannot be, x dot cannot be, x dot square cannot be negative. That's the thing. V greater than negative, not allowed. Okay, so let's go back here. And then let's look at E2. E2, you see that there are 3 separated regions here, here, and here. where it's again the particle cannot go there. Okay, and then we have a third example of E3. So you can see that I've chosen interesting values, okay, which are more typical. So E3 I have chosen to be, say, higher than this peak in the middle, and so here you see that again we are back to having two forbidden regions, and the regions which I have shown in the blue lines here are where it is the particle can. Then I have done a little bit more. So let's look at a point like this. What is happening at this point? E is equal to V of x. So x dot is 0. Okay, so these are called turning points because what happens is that if you look at it in terms of time, so let's say the particle had negative x dot, it's moving this way. It will come this way, and after it touches this point, it comes to this region in space, its velocity is 0, and then it will switch and come back. So these are called turning points. Okay, so now, so if you come to this guy, there are two turning points, and so if the particle is placed like this, then you can see from this thing that it will have some x dot, and so we have to give a direction also. We'll do that a little later, but okay. So then what will happen is that it'll keep going back and forth, and it will be periodic, not simple harmonic, but periodic motion in general. Similarly, if you place it in this region with this energy, then it will stay in this region. Okay, but there is no way for the particle to go from here to here. If it starts off here, it cannot go here. And I keep saying classically it cannot go, but quantum mechanically there is a process which all of you know called tunneling, and it can go with some probability. If you wait long enough, it can happen. Okay, so is this clear? With E2 I have shown you. Okay, so this is what happens. But there are some special values which which I didn't discuss. So let's look at that. So let's look at E4. Okay, E4 is special. So you can see here at E4, I have not drawn a great job. It's supposed to be tangent to this thing, which is the way I'm showing you with my green line. You can see that, right? So what's happening here is that these two turning points, if you wish, collide and meet here. That's what is happening. Okay, so this is a very special thing. Similarly, E5 is an energy where it is very special. And there's actually one more which I didn't show, which is, we can call it E0 if you wish, where it will touch here. So whatever you say, you will find that if the energy of the particle can be never less than E0, which is the minimum of the potential. So we'll have E0 less than. Okay, so E0, E4 and E5 are very special values because, so you can see for E less than E5, greater than E4, there are two regions. But if E is greater than this thing, there's only one classically accessible region. Okay, so these, so you can see that E4, E5 actually separate two kinds of motion. Okay, so I'll pause here and ask for comments or whatever.
So, for E4, if the point particle is placed at the tangent line meeting, the particle will be at rest too.
It won't be at rest. So if let's pick a point here. It has energy E3. It has energy E2. And the potential value is this. So from that up to a sign, you know x dot. So you just have to say which sign. E is given.
I was asking for E4.
For E4, it does,
with the tangent line meets the curve. If we place the point, a particle at that point.
Yeah, so we'll discuss that. We'll discuss that later. Okay. Yeah, what happens there? So if it is there at that point, it will remain at that point forever. Because E equal to V of x. So x dot will be 0. And that's it.
So would it be correct to say that the tangent point is similar to the Lagrange points in the orbit motions?
No, Lagrange point is something very specific. This is more like the ones we discussed yesterday. It's more like the fixed point.
Okay, sir.
Sir, what did you mean by E4 and E5 separate two different motions?
So for E less than E5 and E greater than, just above E5, there's only one accessible region, classically accessible region, the blue line. For E less than E5, there are two accessible regions, two separate regions.
Okay.
All right, so that they are different motions. So for E less than E4, we have to specify, is it in the left part or is it in the right chamber? We have to say that, no? So that's extra. So that's what I meant. E5 separates these two kind of motion.
So,
Yeah.
if it is at E2 and it is at one of the turn points, so what will happen if it is at the previous one, where there is a hump in the E2?
Mm-hmm.
So,
Yeah.
will it be able to cross it, or what will happen if the particle is at that turning point, where there is a maximum?
Mm-hmm. Yeah, what will happen? You tell me.
Will be, I think it will be at that position.
Oh,
At that
okay.
point,
No, that's not what will happen. So let's say it's here. If you place it here, it will start coming this way. Okay. We'll see. We're going to draw the trajectories next. Okay. So that's what we're going to do next. Okay. So it's not the same as placing it here. Because, see, the point is that at this point, it's not as if the force is zero, no?
Yes, sir.
So if you place some particle, the only way it will remain there, it will be slope is zero. If the force is zero, that means dV by dx should be zero. But there is an angle.
Yes.
Okay? So that's why, I just draw that. Okay, good. Yeah. So I think for E equal to E1, we see two turning points, call them L for left and R for right. The particle exists, this is something I've done, but we can work out what the time period is, okay? So we'll just call the left and right turning points X left and X right. And so a full orbit would be, it starts from X left, it goes to X right, and comes back to X left. So what I'm doing here is putting a factor of 2 and just saying, I'll just consider from X left to X right. There is symmetry in the problem. You will see that X right time taken to go from X right to X left is the same as prove that. Okay, so 2 times integral XL to XF dx by dt. So how does this work? I write it like this. Okay, so but we have an expression for x dot, and now I've chosen it. It's going from left to right, so this you will have to choose the plus branch factor. If you're going from right to left, you choose the minus branch factor. So this is a formal integral, and I've asked you to prove that t left to right is equal to t time taken to go from right to left. Okay, so this is the formula for time period. Or given that way, so we have to specify the energy. We have given this. Okay. So we may or may not be able to do this integral, but at least formally this integral exists. Is this okay? So important to realize that periodic is not the same as a simple harmonic. Simple harmonic is very special. Okay, that the time period is independent of the amplitude. Okay, where in these cases that's not true. Generically, it's not true. Periodic doesn't mean that. Okay, so again, I've explained this. For E equal to E4, the energy is special. It is this value of energy that separates two kinds of motion. Okay, so for E less than E4, there is only one segment where the particle can exist with energy E. So these are all things which I have just said, and so I think I will pause here. And so are all these statements clear to you? I've already said it.
Yes.
Okay. Good. Okay. So now what I'm going to do is consider, I will say E1, E2 or E3. Okay, so these are the easy ones. And so now whatever, first let's consider E1. Okay, good. So I consider E1, and then you can see that I've drawn some trajectory. And key point is it's just a closed curve. We know it's going to be periodic, but it's not necessarily an ellipse. Ellipse again happens only for simple harmonic motion. Okay? So this is not meant to be an ellipse, but now the point here is how do I figure out the arrow? It's very easy. So this what we have on here is X and P. So what we have, so if you pick a point like here, what is the value of P here? It is some positive number. This is the axis. This is the P axis. Okay. So what will happen is if you pick a point here, if P is positive, the particle will move in the next instant in the right direction. So this is how you draw the arrow. So you can see that it will be consistent everywhere. So in particular, somebody asked a question, what happens here if I'm here? This says you have to move to the right. That's what I said. I drew that. Okay, so it will just execute periodic motion. Next, take E2, and I just draw. So these are the two turning points. So at these two values, P is 0, and then I just draw some closed curve. Okay, so again, it's a closed curve. But for E2, there's a second segment which comes here, and it is given like this. Okay, and it's easy to see that at these two values, these two turning points, the momentum is 0, but if you come to here, the magnitude of the momentum will be something, and there will be symmetry about flipping about the x-axis because it's just the negative square root. One is a negative square root and the other is a positive square root. Okay, now comes the E3 case is more interesting, which is this guy. So there are exactly two turning points, which are this and this. But now, so what happens is that the P value will increase, but you note here there's a hump here, this hump. So there will be some slowing down because some, potential energy is eating up some of the total energy. So you will see something like this. So this dip is due to that. Okay, so you get something like that. So I'm just showing. So these are the three red trajectories corresponding to E1, E2, and E3. Is that clear?
So can you explain the point where we have a local maximum?
Yeah, so at the local maximum, that's here, right? Okay,
yes,
so this will be where this fellow, the P value will be the smallest. This picture is not so great, but why is that? Because we know that E equal to, I'll write it in terms of P if you wish. Actually, I should write X dot. Let's make it X dot. I don't want it to. So this number doesn't change. It's a constant of motion. So if you see here in this whole trajectory, if this takes its maximum value, this will take its minimum value. Right? Locally there in that region. So that's what I'm showing this dip here. Is that clear?
So this trajectories are asymptotically approaching that particular point, right?
What perpendicular point?
No, this point. I mean, we see that
this point is nothing special. I mean, it's just that the value of X dot or P will reduce. And it'll, again, once it goes to the other side, it doesn't stop there or take infinite time. It will take some finite time to go through. Okay? So now let's look at the case of, which one have I drawn here? Let's look at E5. I think I've drawn E5 out here. Okay. So E5 is the interesting guy. So E5 has this particular point. Let's use a different color. That's black. Okay. So if you come to this point, this is a point where dv by dx is 0, right? It's this thing, and also p x dot is 0. So here is a case where this point itself is a full phase trajectory. Okay, so in dynamical systems language, this is a fixed point. Okay, so then comes now we can talk of things which are if you put the particle here, what happens? Okay, so what it does is that depending on the sign, let's say we give it negative sign, put it here, it's a negative thing, so it will start in this curve, it will start somewhere here. It will go like this and keep asymptotically approaching. And for the same reasons we discussed last time, it will take infinite amount of time to get to this point. We can prove these things, but okay, so it will go like this. So what is happening? And similarly, if you start on this side, and if you give it this kind of momentum, then it will start somewhere, say here, and it will proceed like this and go there. Okay, again, so actually this magenta curve. The magenta curve is actually 3 trajectories. One is the left trajectory, left lobe. The second one is the black point, and the third is this thing. Okay, so this black point has a name. Okay, so the trajectory for E5 does not cross the x-axis in perpendicular fashion. So one more point to note here is that whenever these trajectories cross the x-axis, generically you will find that you can prove that the slope of this curve is it's perpendicular. Okay, so it's so slope is infinity. Okay, but at this point this is not true. Okay, and need not be true. Okay, so I'll read these things. So consider this thing. So the generic. Yeah.
Can you please repeat the last point you referred to?
I'll read this through the whole thing, and then it will be a repetition. Okay. So I said consider E1, E2 or E3. The phase trajectory is always a closed curve. Trajectory crosses the x-axis perpendicular to it. Why? And this is homework for you. You can prove it. Okay. And then the trajectory for E5 does not cross the x-axis in a perpendicular fashion. So that's not true for E5. Okay. And the point also appears to be self-intersection. But okay, so this black point has a name. It's called the separatrix.
So when you say perpendicular, what is perpendicular to what?
The curve, the tangent to the curve. So you pick one of these red curves and see how it crosses the x-axis. Okay. At that point, you ask for the tangent to the curve, and the tangent will be infinity. Okay, it will be making 90 degrees angle. Okay. So what one is saying is, you think of x dot and x as independent variables, slope will be d of x dot by dx for the curve is equal to infinity. Okay.
Sir, in this diagram, there is no such perpendicular thing, right?
Oh, there are plenty, no? 1, 2, 3, 4, 5, 6, 7, 8. Except
Okay.
for this black point, which was there in the previous slide. Okay. So I'm just saying such points are called separatrices. It takes infinite time for the particle to reach it. Can you mute yourself? Okay, good. If you can use headphones, it will be nice, because then what happens is that we don't get feedback. So otherwise there is feedback. Okay, so now again we will look at fixed points, and so fixed points and types of equilibrium. This we saw last time itself. The fixed points of Newton's equations correspond to points in phase space with P equal to 0 and the extrema of the potential being dV by dx equal to 0, and that's exactly our separatrix was one such point. So in the dynamical systems language, this black point is a fixed point. Okay. And in the example that we just studied, there are 3 such points in phase space. Okay. And there are 2 points of stable equilibrium where d square v by dx square is greater than 0, and points near these two fixed points correspond to periodic orbits and remain in the neighborhood of the fixed point. Small displacements from the fixed point lead to a restoring force. The third point is the separatrix, and this corresponds to unstable equilibrium. Points nearby can go off in completely different trajectories. That's something which is very easy to see. So let's just pick a point. So this is the separatrix. So if I pick a point here, or rather let's take a point here, it will just go off. Similarly here, if I pick here, it goes off to a different trajectory. So the whole point here is that so this is unstable. Okay. So what is happening is that the stability turns out. So first thing is to get a fixed point, we have to the problem becomes simple. We just have to look at minima, not minima, extrema, dv by dx being 0, and that is exactly 3 points for this guy. And then you look at this as a second derivative at these points, which is the curvature. So if it curves upward like this, these two are stable, and if it's this thing, it's unstable. So the unstable point leads to the separatrix kind of behavior.
Use the arrow while denoting points.
What?
Please use the arrow while denoting points, because
I don't use arrow for denoting points. I use x cross, because arrow is the direction of propagation.
Means the arrow of the bar.
I don't understand actually. Repeat what you say.
Sir, I think
The arrow that you move on the screen.
So can you use a darker color because you might be moving? Yeah.
That
You're not able to trace the points, that's why. If you use the arrow on that screen, that one, arrow on the screen.
I don't know how to get arrow on the screen. I told you I'm learning how to use this.
It was there, it is there in the side, that's why.
Where side?
Is he talking about the cursor?
Yeah, there's no cursor. I don't. Cursor is on my mouse. You're saying use this. Okay. Okay. Yeah. So I have a pen in my hand and not a mouse. So okay, that's a complete. I can do that. Okay. Yeah. So this is the separatrix point, and so these 2 points are the stable lines, and this is unstable. And now, okay. But you can have a third kind of equilibrium, neutral equilibrium, that does not appear in an example, of course. You can have a potential which is like this. It's not, so there's a flat region here, you see. So here you can see if I keep it here, it will remain there. If you push it a bit, it will continue to remain there. So, okay. So these are the 3 kinds of neutral equilibrium. So one more exercise is to go back and ask from the viewpoint of dynamical systems, how does things which we just said here. It just says we have to look at the second derivative, etc. You can check that it agrees with our notion from general dynamical systems. Also, we looked at the same story. Okay. So.
Hello, sir.
Yes.
So can you once repeat what will happen if the particle is at fixed point?
If it's at a fixed point, it will remain at the fixed point.
Because
that's all. Because look at it, right? P equal to 0 and dv by dx equal to 0. This means force is 0 and it's at 0 now. So it will remain there. That's why it's fixed point for Newton's equation. That's the definition of fixed point, no? What else do you want beyond that? But the nature of equilibrium is not that, is to look in the neighborhood of this thing. So either you keep P equal to 0 and push it by X a little bit, or things are usually in dynamical system we do it in phase space. So here we just did it in what do you call real space, and we just say we keep P 0 but we move it a bit. Nothing happens. So this is what we call neutral equilibrium. Okay. Okay, so now we will do a very simple problem. It's a problem that you have studied in high school. Okay, so we consider a simple pendulum consisting of a string of length L, okay, massless string, of course, connected to a bob of mass m that is restricted to move in the xz plane with gravity acting on the z direction. Okay, so the kinetic energy is just half m x dot square plus z dot square. So here is an example where, the coordinate, it's better to choose a different coordinate. Natural coordinate to choose is the angle theta with the vertical. So the picture we have is something like this. So from this you can just see that this is so this xz, right? So this is the x is this is x, so x is L sine theta, and z is L minus L sine theta. So where theta is 0, it becomes so that's my 0 is chosen that way. Okay, so you can see I'm just saying this is x and this is z. And we want to do x dot, and theta is the only thing which varies with time. So if you just put it in there, you get a nice kinetic energy term, which is just ml square by 2 theta dot square. So it's something which you know. And potential energy is mgz. So you just go ahead and put in the value of z, and so this is what you get. Okay. So now, so usually what do? We say that, and so, what did I do? This happened last time also, right? So let's get out of here. Different files. Looks like we lost all the things that I had just done. This is not fun. Is there a way to go previous? So we lost all the annotations I had done, right? Just 1 second. I'll see if I can recover it. Okay, it looks like we lost it. Okay, so just draw at least some picture again. Like I said, I'm trying to figure out how to use this. Clearly, I'm doing something wrong. I have to figure that out. Okay, so now the point here is that we have V of theta is mgl into 1 minus cos theta. So you have to specify the initial energy. So you'll have two turning points. So theta naught plus or minus theta naught are the max and min values. Of theta fixing given E. And you can check that the energy is given by this formula. Because at those points, all the energy is potential energy, so you just put theta. So this is the energy. So you go back to the time period formula which we had, which was E minus some, if you remember, there was some dx by E minus v. So if you plug that in, you will get this nice integration. T equal to 2 times root L by G from minus theta naught to plus theta naught with this integral. It's easy to show. Basically, we have to work out E minus V of theta. So E is given by this formula. You see the thing, this MGLs will cancel out, and it will be just the difference of those cosine theta. And this guy is has the correct dimensions of time. Okay. So this is what we get. For small oscillations, we can just go ahead and substitute cosine theta equal to 1 minus theta squared by 2, and then you just do some change of variables. So that means small oscillations, that means theta naught. Okay. By the way, for me to use this formula, what should theta be in?
Radians.
Okay, very good. Okay, so we don't do degrees. Okay, theta is in radians. So theta naught also in radians must be much less than 1. And then you can do this integration, and then we get to the integration will give 2 pi. Okay, so that is our usual time period of a simple harmonic. So the of the simple pendulum for small oscillation. But we are now grown up. We want to ask what happens when the amplitude is not small. You cannot use the full formula. And you can, if you want, we can write this kind of cosine theta identity, and you will still get this integral. And the point here is that this can be written expressed in terms of what are called elliptic integrals of the first kind. Okay, so you might see this. So these are some new special functions. Okay, and then you can also do things like you can do some expansions, and you can some series. So then you will get T by T naught is to be, so this is 1 for small oscillations. Then there are corrections. So first one is 1 by 16 theta naught square plus 11 by 3072 theta naught power 4 plus dot dot dot. Okay, so can you reproduce the first term, for instance, first one? Okay, so I just leave it as an exercise. Okay, and so Gauss had actually 2 approximate formulae that work reasonably well, and I just state them. T by T naught is 2 into 1 plus cosine theta naught. T by T naught is also 2 plus divided by 1 plus square root of cosine theta naught whole square. But there is something which is very interesting, is that when theta naught equal to pi, okay, what is that? That means you're taking it and putting it almost vertical. Okay, the integral can be done, and we obtain T equal to infinity. What does that mean? Let us try to understand that. Okay, so first thing is, it's easy to see that theta equal to 0 and pi are extrema of the potential. Theta equal to 0 is the stable point, while theta equal to pi into E minus 2mgl. Theta equal to pi, that means E should be this particular value, is unstable. Again, you can check this thing. So it's in fact a separatrix, and it separates oscillatory motion for E less than this thing to circular motion for E greater than 2mgl. So the point here is, if you have this pendulum like this, so oscillatory motion is something like this. Rotational motion is where this goes around like this. It went out of the screen, but you understand what I mean. Okay, so if energies are greater than that thing, it can overshoot and come. Okay, so when E equal to 2 mgl, we can actually do the first integration and get this answer. Okay, again, this is an exercise. You can do this integrations and you can get. But it's only you can do this when E equal to 2 mgl. Oh God, again. Okay, so what I will do is there's a very nice on Moodle. I will share an article which discusses the Arch oscillation, how to do calculations. Okay, so I suggest that you read that article. It's a beautiful article. It shows you this thing. It may even tell you how to do this particular computation, for instance, which is how to get this. But this, I think, you should be able to do. You just have to, yeah, I won't say anything. So you can try to. So what I want you to do is to get at least 1 by 16 theta naught square. That's an exercise. Okay. So I'm done with my lecture for today. So the point here is that is even for a simple pendulum, which you think you know quite a bit about, you will find that there is much more structure once you start going beyond small oscillations. And at your level, you will be able to understand it and appreciate it. So yeah, the floor is open for questions.
So in the last slide, can you please switch to it? So in the last most. So when we say theta naught is equals to pi, it would be a fixed point and the particle won't even move. Would it be reasonable to say that the time period is infinite?
Yeah, that's why we get infinity. That's why you get that.
So it just stays.
Even the approach. No. If you start with that thing and it starts out here with that energy, it will keep going, and it will asymptotically reach vertical, but it will never reach.
Sorry, sir. Can you repeat?
If E equal to 2 mgl, which is what you get. So, but I can start it somewhere here.
Okay,
at
sir.
this point with that energy. Then it will go up and it will reach here.
I get that, sir.
But it will take infinite time to reach that. But if you start out at theta naught equal to pi and theta naught equal to 0, it will just remain there.
And then it would not be reasonable to say time period is infinite.
Yeah,
Okay,
there's no, nothing. It's just a fixed point.
Okay. Thank you, sir.
Sir, at theta naught equal to pi, wouldn't it be just free fall motion from the top point?
No, not if, what we are saying here is that, so you think of it as being held with some massless rod and it's kept perfectly vertical. Okay, then it will remain there. But what happens in real life is there will be perturbations, right? There will be some air from my fan coming or something. It will just give it some little bit of a kick. And then it will go off, like you're saying. But here we have not put those things in. Those effects are not there. We are just saying it's ideal, simple pendulum. So if you keep it with a rod and with a mass at its end, it will remain there.
Okay.
Okay. If it is held with a string, then that won't happen. Right? String, it will just fall. String can't hold it, so it should be some rod.
Yeah. I was assuming string only. So.
String, it will just fall. Because tension will, you have to keep the tension which is needed to keep there. So if it's a rod, that tension will be there. Any other questions? Okay, so I'll stop sharing.
So in that slide 8, you referred to that for stable equilibrium, only one of the functions you consider, Vx but the other function P also should be considered.
Yes, yeah. I said go back and look at. Absolutely. Yeah. So you need to look at P equal to 0.
Yeah. For stable equilibrium, you have to consider dP greater than 0. That condition also should be.
Yeah. So go back and do that. Do it from the viewpoint of dynamic resistance. Okay? Yeah. I left it as an exercise. Okay, so let me stop recording.